ladies and gentlemen, usually when we're doing the SDS page labs, I have an opportunity during the lab to actually have a little chalk talk about some of the concepts of units, specific activity, etc. This week, because we're adding in the dot plot, we've got a few other experiments to do, I don't really have that opportunity during the lab. So what I'm going to do is this video, which will hopefully clarify some of those ideas. So I'm going to start with the idea of units. Now, the units of an enzyme are specific to that particular enzyme. It's not a metric measurement. That means that the units of restriction of nuclease are the same as the units of lacZ, are the same as the units of alkaline phosphatase. Instead, it's defined per enzyme. So the units of a restriction of nuclease may be defined as that amount of enzyme which is required to digest X amount of DNA at a certain amount of time under standard conditions. Now, the standard conditions part is important. In order to compare from lab to lab, the pH has to be the same, the reduction has to be the same, the concentrations have to be the same, the temperature has to be the same. All of these things affect enzyme reactions, so of course being consistent allows you to compare. Now, for lacZ, we are defining 1 unit of lacZ activity as that amount of enzyme which will digest and process 1 nanomole of ONPG per minute under standard conditions. Now, we did our assays under standard conditions, so you don't have to worry about that part anymore. So, one nanomole per minute. Now, how do we get that value? Well, it's easy when we go from our ONPG assays, which is exactly what we're determining. From our ONPG assays, we did an absorbance reading. It gives you some sort of absorbance, right? You then have an extinction coefficient. So when you put those two things together, okay, obviously you don't just add them together, I'm just indicating you put them together. You can achieve a concentration. Now, concentration will be determined, well, the value of that concentration, the units of that concentration will be determined by what the value of the extinction coefficient is. All right? Now, we have a concentration. So far, so good. We need to go from a concentration to a number of nanomoles. For that, we need a volume. Now, volume that you're going to use for this is not the 1 mil you put into the cuvette, rather it's the volume of the whole assay. Okay? In most cases, 1.4 or 1.45 mils. Okay? By multiplying those two together, you'll end up with a nanomolar amount, or you can convert it to a nanomolar amount. The last thing we have to do is divide it by the number of minutes. Now, you ran your assays for 5 minutes before stopping them with the sodium carbonate. By dividing this value by 5 minutes, you determine the number of units that were in the assay, that were in the 1.45 mils of assay. So far, so good. Now, that's how we determine the number of units in a given assay. Now, you know what volume of whatever reagent you put into that assay. Was it 50 microliters of bacteria? Was it 2 microliters of cleared lysate? Was it 10 microliters of purified protein? From that, you can ultimately work out the units per microliter of whatever substance you put into the assay. Okay? So it's just units over whatever volume you add into the assay. From here, from units, we're going to talk about the idea of specific activity. Very straightforward. All this is units per milligram of protein. Now, we couldn't determine this last week, but this week we're doing protein assays on our cleared lysate and on our purified protein. From that, we can work backwards to a specific activity. So, we can already determine from our ONPG assays the units per microliter of, say, our cleared lysate. Okay, so let's take an example of our cleared lysate. Let's say it's got 10 units per microliter. Now, this may or may not match up with the value you found. That's fine. Today, or this week, pardon me, we determined using a Bradford assay that your cleared lysate has 1 microgram of protein per microliter. The specific activity of your cleared lysate, therefore, is just 10 units per, 1,000 units per milligram. Okay? So if you have 10 units in a microliter and 1 microgram per microliter, that's 10 units in a microgram. So the number of units you have in a milligram is 1,000 times bigger. Okay? So that's looks like a good specific activity. Let's do the same example about using your purified protein. What we're hoping is, with your purified protein, is you will have lost some of your units, but hopefully you will have lost a lot more of the extraneous protein. So you might find from your purified protein that you find that you have 5 units per microliter. Again, your values may be different. From our Bradford and or our UV spectrophotometer this week, you might determine that the amount of protein in your purified protein was 0.01 micrograms per microliter. And that's entirely possible. From there, we can get a specific activity for our purified protein. The higher the specific activity, the more pure that enzyme is. So, 5 divided by 0.01 is 500, times 1,000 to get the units per milligram. So we've got 500,000 units per milligram. So here we have a specific activity. Let's slow that in. Here, before purification and after purification. This leads us up to the next concept, which is the fold purification. All it is the ratio of your specific activity after purification divided by your specific activity before purification. In this case, we can use this example again. After purification, let's say we have a specific activity of 500,000. Before purification, we have a specific activity of 10,000. 500,000 divided by 10,000 is 50. What we then say is we have a fold purification. In fact, if you don't mind, I'm going to erase this, put this up on the board. Of 50. So here's our little formula. Fold purification, specific activity after versus specific activity before. Let's do fold induction. This is even easier. What I'm looking for here is how much more lac-Z activity is there in your bacteria after 45 minutes in IPTG. Well, that's very straightforward. In fact, you could work out the actual units per mil or microliter. You could work out the specific activities. You could work out the units per volume. It's actually even easier than that. You did an ONPG assay on 50 microliters of bacteria after 45 minutes of induction, and you did an ONPG assay on specific on your bacteria before induction. You don't even have to use the extinction coefficient. Because of Beer's law and the relative linearity of our ONPG assay, and all you really need to do is compare your absorbance after versus your absorbance before. This isn't probably the 100% most correct way to do this, but it is the easiest. So I'll just put your A, your absorbance after, divided by your absorbance before. So, as a trivial example, let's say after induction, you did your ONPG assay, you did your cuvette in the spectrophotometer. It said you had an absorbance of 2. Before, it said you had an absorbance of 0.5. Your fold induction is 4. It's that easy. The last thing I'm going to talk about is percent recovery. Now, I need a little bit more space. So if you don't mind, give me a second to look at this. You can always come back to it. And I'm going to give myself some room. Percent recovery is basically just how many units of enzyme did we have in our purified protein, how many units of enzyme could we have had in our purified protein. So we need to know what was available to us to be purified and what we actually purified. So let's work out how many were available for us to purify in the first place. From that, we're going to go back to our cleared lysate. So imagine this is our tube of cleared lysate, label it CL. You did an ONPG assay on a volume out of the cleared lysate. Using that, I want you to work out the number of units per microliter in your cleared lysate. So if you assayed 10 microliters of cleared lysate, divide your units by 10. If you assayed 2 microliters of cleared lysate, divide it by 2. Once you know the number of units per microliter, we have to figure out how many units of lactate activity could we have actually isolated. Well, for this, we have to go back to the volume of the cleared lysate. We know how many units there were per microliter, per volume, but what was the volume? It was 1 mil. So whatever value you have here, multiply it by 1,000. Okay? So your percent recovery, one of the values we're going to use is the number of units in 1 mil cleared lysate. I'm just going to use CL. Now, you can very easily change this up. I'm just going to erase that. Let's go back to our purified protein. You assay 10 microliters of purified protein, determine the number of units in that, divide it by 10, get the number of units per microliter of purified protein. We then go back to work out how many units total did we actually get in our aliquots to freeze down, or we used. Well, for that, we have to go back to the volume of our purified protein, which in this case was only 50 microliters. So, whatever value you find here, multiply it by 50, that was the number of units you had at the end of your recovery process. Okay, so far percent recovery is the number of units in our 50 microliters of purified protein divided by the number of units in 1 mil of cleared lysate. We're only missing one thing. We have to turn it into a percentage. Okay, multiply whatever this value is by 100, and that's it. And so that runs us through units, specific activity, full purification and induction, and finally, percent recovery. All of these I'd like to see you incorporate into your results report. They're all good values to calculate when doing recombinant protein extractions. Gives us a very good idea of what kind of success rate we're having with our enzyme extractions and where we might improve.